All right, today we are going to learn about half-life and how to apply that. So we need to understand what half-life is. So half-life is the time required for any special property to decrease by half. Okay, so we're looking at, oops. There we go. We're looking at anything that's going to be cut in half, right? So how long does it take to get cut in half? And then we go from there. And so there's a special formula that we're going to use to solve all these equations. And that formula could look a little different, but I like saying y is equal to a times, and then the b value is always going to be 1/2 because we're talking about half-life. It's going to be decaying by half every so often. And then it's going to be raised to the power of the time divided by how long it takes the half-life to occur. I've just been using the variable n. Some people use the variable h or something different, but I've been using the variable n, so I'm going to stick with n for right now. Okay, so in this equation, y represents the final amount, a represents the initial amount, the decay factor is always 1/2, and then t represents the time, and we'll say n represents how long it takes that half-life to occur. Okay, so we'll come back to this equation here in just a second. So if we look at number 2, this is kind of a really easy, good example of how half-life works. So we can do most of these in our head. Number 2, starting off. So it says, if you have 100 grams of a radioactive isotope with a half-life of 10 years. Okay, so that means it takes 10 years for this radioactive isotope to be cut in half. Okay, so then it says how much of the isotope will be left after 10 years. So after a 10-year period, this original 100 grams is now 50 grams. So that's how much is left after one 10-year period. Okay, then it says how much of the isotope will you have after 20 years. So again, we take what's left was the 50 grams, we cut that in half, and we have 25 grams. But then problem C says how many half-lives will occur in 40 years. So we have to figure out, right? We have to figure out how to solve that without having to go through that process of, oh, it got cut in half 1 time, 2 times, 3 times, 4 times. And so this is where that formula comes into play. So again, here's my formula. Okay, this time I'm going to use a decimal just to show that you can also use a decimal. And then what I need to understand is that 100 is my initial value, which is my a variable, and 10 years is my half-life, so which is represented by n. And so I am simply going to substitute those two values in to my equation, and this is how I would find those final amounts. Okay, so my final amount in part A is 50 grams. How did I find that? I did the 100 times 0.5 raised to the power of 10 years, because now it tells me 10 years have passed, divided by the half-life of 10 years. And that's what gave me 50 grams. Same thing for part B. I did 100 times 1/2 raised to the power of 20 divided by 10 this time. And so if I want to figure out the final value, which is y, with an initial value of 100 times 0.5 raised to the power of 40 over 10 in 40 years, then I would simply calculate what the value of this is. And I could do that on my calculator. I could do that on Desmos. So I can simply just do 100 times 0.5 raised to the power of 40 divided by 10. And that gives me a total of 6.25. So the final value after 40 years, so the Y is my final value, is 6.25 grams is what is left. Okay, and so that's how we use that equation. So in the next few problems, 3 through 8, I am simply just going to write the equation first, and then I'll come back and solve it. Okay, so for number 3, as I read this, I'm going to write down what variables are represented by what. So it says the half-life of plutonium 239 is 24,300 years. So this is my N variable. If a nuclear bomb was released 8 kilograms, this is my initial value, of this isotope, how many years would pass before the amount is reduced to 1 kilogram, which is my final amount, which is 1. So this is saying how many years, right? How much time will pass? That's my T. So I use my equation. I have Y equals A times 1/2 raised to the power of T divided by N, and I substitute. I know what my Y value is. It's 1. I know what my initial value is. It's 8. I know what the value of N is. It's 24,300. And so this is the equation I'm going to use here in a little bit to solve that problem. Okay, same thing with number 4. I'm going to start with my final amount is equal to my initial amount times 1/2 raised to the power of T divided by N. The half-life of radium-222 is 3.8 days. So this is N. How much of a 100-gram sample, initial amount, is left after 15.2 days? Time. So this time, again, I know my initial amount, 100. I know my time is 15.2. And I know my half-life is 3.8. Okay, and again, I'll come back and I will solve that here in just a second. Okay, number 5, again, Y equals the initial value times 1/2 raised to the power of T over N. Okay, so carbon-14 has a half-life, so that's N, 5,730 years. If a sample contained 70 milligrams A originally, how much is left after that many years? Is T, 17,190. And again, I know N, T, and the initial. So 70, 17,190, 5,730. Yeah. All right. Then number 6, a half-life of cobalt-60 is 5.26 years in. If 50 grams are left, okay, so this changes things. 50 is my final amount because that's what's left. If 50 grams are left after 15.7 years, which is T, how many grams were in the original sample, which is A? So this time I know the final amount. I don't know my A value. B is always 1/2 with half-life. And then I have 15.78 over 5.26. So that equation is what I'm going to use to help solve this. And then number 7, okay, we have a half-life of 8.07 N. If 25 grams are left, that means that is Y. After 40.3 days, how many grams were in the original sample? So again, we have 25 is equal to A times 1/2 raised to the power of 40.35 over 8.07. And then number 8, if 100 grams A of AU-198 decays to 6.25 grams, which is Y, my final amount, in 10.8 days, T, what is the half-life of AU-198? So we have the final amount is equal to the initial amount times 0.5 raised to the power of 10.8 divided by N. Okay, so that is all my equations. Okay, so this is the most important part. If I can set up my equation, then I should be able to solve these problems. So, all right, so I'm going to group things kind of together, and I'll just probably work one at a time. So the first two that are similar, that are the easiest to work, are numbers 4 and 5. So I'm just going to work, I'll work number 5. Okay, so here we notice that we have an equation and it has y equals, and then everything was substituted into this side. So I just need to find the value of this side right over here. And so in order to do that, okay, I plug that into my calculator or even Desmos. So I have 70 times 0.5 raised to the power, and then I just put in the correct power, 17,190 divided by 5,730. And so it gives me my answer. Okay, even if you were to put in y equals, right, and then I put in that equation, it would still give me my answer. So my final amount left after that many years, okay, was the 8.75. So y is equal to 8.75 grams. Okay, or sorry, this is milligrams. All right, and then you would solve number 4 the exact same way. Okay. The next two that are similar are numbers 6 and 7. So 6 and 7 are the exact same, okay, because we don't know the initial amount. Okay, and so what I'm going to do is I'm going to create 2 separate equations. So I'm going to take the left side of my equation, which is 50, and I'm going to plug that into Desmos. So I do y equals 50. So that's one equation. And then I'm going to take the entire right side and I'm going to plug that into a second line for a second equation. So this time in my second line, I have y equals, I can use a or x. If a doesn't work, go ahead and use x, times 1/2 raised to the power of, I believe it was 15.78 divided by 5.26. That's what I believe it was. Okay. 15.78, yes. And so now all I have to do is come over here to my graph and kind of find the intersection. So I'm just kind of zooming out right here. And so there's my intersection. It happens at an x value of 400. So my initial value, that a value, is 400. And so the initial value is 400. Okay, and this one is grams. So 400 grams is what I started with. And then you would do number 7 the exact same way. Okay, and then I'm going to actually do the other two that are similar. Is number 8 and 3. I might do both of these, okay, because 8 doesn't work out. It works out kind of easy, but then 3 works out very difficult. Okay, well, same thing. Actually, I'll just do number 3 since it works out difficult. So Same thing right here. I'm going to split this up into two different equations. So y equals 1. Okay, y equals 1. And then this entire side, y equals 8 times 0.5 raised to the power of, it was t or x divided by 24,300. Okay, and so that graphed. If it didn't graph because you had a t, then go ahead and put an x. Okay, and then here's my problem. Most of you guys are going to see this. All right, and so two ways I'm going to kind of teach you, right? We just got to think common sense wise. Why does it look like this? Okay, so one, this first equation, the black one, should be a horizontal line. The red line looks horizontal, but that's just because of this big number, 24,300 right here. And so I need to figure out, like, where is my intersection going to happen? Well, all these values are probably going to be positive. So it's going to happen way down here. But when I start zooming out, like, that doesn't help me very much. Okay, so I need to change the domain of this. Okay, to change the domain, basically how far I see to the right without having to adjust the range, right? I'm going to click this little graph settings button up here, and the x-axis is my domain. So I want to change this number right here to a really big number. Okay, what I basically do, especially if I have a really big number, is I just start with 1, and then I just start adding zeros until I see my intersection. And so now I can click on there and then find my intersection. So it happens in 72,900 years. Okay, so that is my answer for number 3. The time it takes is 72,900 years. Okay, now I told you I was going to show you another way to do that. Okay, well, let's think about this problem logically, right? It says we started with 8, right? And I want to get to 1. Well, we know things are getting cut in half, and I can do this because, like, this is a common sense problem. You can't do this with all of them, but this also helps me estimate, like, the domain I needed to use. So let's say after one cycle, right? After one cycle, I would have 4. Half of 8 is 4. That takes 24,300 years, so about 25,000 years. Then if I do another cycle and it gets cut in half again, it would go down to 2. Again, that takes another 24,300 years. And then again, another cycle is another 24,300 years. So there are 3 cycles to get down to our final answer. So this one works out nice and neat to where all I need to do is add up that 3 times. Okay, but even if it didn't get this number exactly, then this would help me understand my domain. So, like, I could round this to 25, 25, 25, so that's 75,000. So on my Desmos, if I were adjusting my domain, I could come in here and do 75,000, and you could see, like, hey, there it is. It's now on my screen, so it's pretty close to 75,000. So that's just how I use the common sense, right? Okay, and that's Half-Life. If you have any questions, let us know.